So this is my first time actually at Spring One speaking in several years. I guess the last time was in Dallas. And I said, I haven't talked in a while. Let's do a presentation. So we're going to talk about architectures that bend but don't break. And we're going to structure everything as a series of questions. So if we're going to talk about architectures, maybe we might want to know what architectures are. So we'll attempt to define what we're talking about. Answer the question, what does bend but not break mean? Is there any way we can turn the gain down just a little bit? Because I'm practically whispering. What are software stressors? When our software is stressed, how do we want it to behave? What qualities do we want it to have? How do we measure those qualities? It's a pretty important one. How do we know that we actually have the thing that we wanted to get? And then ultimately, how do we go about creating those qualities? So this is the map of where we're going, and we'll keep coming back to it to remind ourselves of where we are. So let's start with, what is architecture? And nobody really agrees on the answer to this question, so I put together some definitions from friends of mine and other people that I respect, and we'll try to come up with something that kind of gives us an idea of where we are. So my good friend Matt Parker, who is also speaking on the agenda this week, he talks about architecture and software architecture. So generally architecture being decisions that are hard to reverse, and then software architecture being this high-level shape and flow of software, independent of the problem domain, dependent on the desired user experience. Another friend of mine, Simon Brown, says that architecture represents significant design decisions that shape a system, and significance is measured by cost of change. Then we have Grady Booch, probably heard of him. This is one of many things that he says about architecture, but I like this particular sentence because I think it adds a lot. That architecture is not just a thing that we make, but it's actually a process that we engage in. And it's a living process. It continues throughout the life cycle of the software. Ralph Johnson just kind of admits that we don't really know what architecture is. On this particular project, it's whatever's important. And on this project, maybe it's something else, but it's definitely whatever's important. And so I kind of tried to synthesize these things into something that makes sense to me. So I like the process part. So architecture is a process by which we make, and I also think really important, capture. So it's one thing to make a decision. It's another thing to be able to communicate that decision. It's still yet another thing to be able to communicate that decision to somebody who wasn't there when the decision was made. So capturing those decisions, they have some sort of a system-wide impact. So it's not, when we're writing a single line of code, we're not doing architecture at that moment probably. We are making decisions, but it's likely that that one line of code probably doesn't have system-wide impact, but the sum total of all of those things do. And then they are often expensive to reverse. I think that's something that almost all of us agree on. So this is the thing that we're talking about. So what is one of those that bends but doesn't break? Which is our next stop on the map. So a couple of pictures of this idea. So Robert Jordan wrote this book, The Fires of Heaven, and there's a quote from the book that says that the oak fought the wind and was broken, the willow bent when it must and survived. So there's a notion here of resistance up to a point at which you can't resist anymore and you break, or we bend and we bend and we bend against all of this stress, and somehow we manage to survive. I'll use a football analogy. Some of you that's going to annoy, some of you are going to enjoy this. But last year, the New England Patriots, they eventually broke in the Super Bowl, but up until that point, they were known as this bend but don't break defense. What does that mean? Well, one of the things that you want to be able to do is limit your opponent's yardage gained. And the Patriots were terrible at this. In fact, they were the worst of all teams in the NFL last season at limiting yards per drive. And yet, they were very respectable sixth in points per drive allowed. And at the end of the day, it's not yards that win games, it's points that win games. And so they were very good at bending really up until just before that breaking point. Of course, that finally caught up with them at the end, but you get the idea. So trees, football teams, we could go through a lot of different analogies. What are we talking about when we're talking about breaking versus bending? Well, if we look at things that break, first of all, there's this notion of fragile things, and we put stress on a fragile thing, and it usually ends up being damaged, if not destroyed. We also have robust things. We put stress on those, and they resist, but again, they resist up to a point. They have a breaking point, and eventually that resistance runs out, and we're back in the fragile category. So we lasted a little bit longer. These are not the types of systems that we're trying to build today. Instead, we want to build systems that can bend. So we talk about this notion of resilience, which basically is we put stress on a thing and it's able to adapt. Now, at the end of the day, again, you can only adapt so much, but we're able to stretch from resistance to adaptation and last even longer. And then ultimately, if there is any kind of damage, it's usually reversible. So this is much better. But we can go further. There's this notion of antifragile, the opposite of fragile. So fragile things, we put stress on them and they are destroyed. Antifragile things get better. We can actually use stress as a source of innovation. Now, I wish I could take credit for this graph, but I can't. I borrowed it. And I think it really shows these four different choices well. And if you look at stress and change as it goes up, the fragile system doesn't last very long. The robust system lasts a bit longer, but eventually hits its breaking point. The resilient system adapts, and it actually is able to benefit and gain. We can do more, but eventually, again, we hit our breaking point. Anti-fragile, theoretically, never has a breaking point. It just gets better and better and better. So, another way of looking at resilience: ability of a system to adapt or keep working when challenges occur. What are the types of things that we're thinking about when we're thinking about resilience? Well, you've probably uttered words like fault tolerance, evolvability, scalability, fault isolation, management of complexity. These are the types of things that we're interested in. And these make sense, right? There's not a whole lot of deep thinking that we have to do to realize these are good things, and as we'll see a little bit later on, there are fairly well understood patterns that we can apply that will give us a leg up on achieving resilience. Now, anti-fragile is a little bit different. Nassim Taleb has written many interesting, controversial, mind-bending books. This was one of them that he claimed was the summary of everything that he had written up to this point. And he talks about systems throughout history where, again, we place stress on a system and instead of it getting worse, it gets better. He talks about things like the immune system. You don't put stress on the immune system. In fact, we are fairly antibiotic friendly in this part of history. And what do antibiotics do? They do the work of the immune system for us in some cases. The more of those you take, two things: A, your system gets weaker, but B, we create more resistant antigens. So when my kids were small, we kept them away from all the other kids, but eventually they had to go to school. And when they went to school, what's the first thing that they did? They got sick. But eventually, after a few grades of school, that kind of tailed off as the immune systems got stronger. Muscular systems, right? We go and we lift weights. Why do we lift weights? Because we want to damage our muscles. We don't actually say that, but that's what we're doing. We damage our muscles, and they rebuild themselves, and they come back stronger. Now, what's also true? If you stop damaging your muscles, then eventually they get weaker. So stress makes them better. Lack of stress makes them worse. We can look at communal organic systems. You've got swarms of ants. Now, an individual ant, not that powerful. But you take a community of ants and you put them together, and they can actually do remarkable things. For example, we throw a bunch of ants into water, and what do? They self-organize, and they create what is essentially a naturally occurring Gore-Tex-like material that repels water. Now, nobody told the ants to do this. It's just kind of built into their nature. One ant, now a couple of those ants, they're piecing out and heading up the tool there. But the rest of them, we can't make it, so join together and we make this material that one ant can't make by itself, but many of them together. Now, when we think about software, how do we do this in software? It seems like we would have to create something that could see stress and make itself better, which sounds suspiciously like Skynet, but I think we're not ready for this just yet. But if we think about the system beyond its boundaries, so we do have, these software systems, distributed systems, things linked together, but we all know that this software does not exist independently of the people who are creating that software. And so if we kind of understand the teams plus the services and their interactions as this socio-technical system, this is something that we can start to introduce antifragility into. Because the way that we actually approach the building and the delivery and the testing of software can be one where we intentionally induce stress in order to actually make the system better. So we'll get to that. So what kind of stress does software have? Fairly obvious things, right? Another friend of mine, Russ Miles, he put together a list of 5. And some of these are more obvious than others, but basically change. So innovation, we want to drive things forward, we want to make things better, we have to change the software in order to do that. The system is wildly successful, we have way more users than we thought we were going to have, and so we have to do what? We have to make the system able to handle more, we have to increase its capacity. The opposite of that, nobody really uses the system, and so we have to reduce capacity, so there's still change there. System failures, I think probably most of you, when you saw the title of the talk, that was the first thing that you were thinking of. Was, okay, here's yet another talk about all the times that software fails, and here's all the ways that we're going to make it not go down. We're going to talk about a little bit of that. And then this last one is kind of interesting, the emergent need to reuse. So this is you working on a software team. You've built a component that is useful to you. And then other people find out about it. And they start using it. And then they tell all of their friends. And they start using it. And before you know it, that little component that you built to meet your needs is now the backbone of the entire company's software infrastructure. Does that ever happen? Sure it does. Is that stressful? Yeah. So these are the types of things that we're thinking about. Now the journey is going to start slowing down, I promise, but we have to do these first steps. So what do we want? We've got architecture, we want it to bend but not break. Here's the type of stress that we're going to place on it. How do we want the system to behave under these circumstances? I'm not going to talk about all the stressors. I want to focus in on really two key categories. We'll start with innovation. So the real question is, can we continuously deliver incremental value to the business through software? As more change comes, products continue to live, what usually happens? We get slower and slower and slower, and in adding that next incremental feature gets harder and harder and harder, and the design becomes less and less comprehensible. Is this not our normal experience? So how do we counteract that? How do we stop the software from hitting this breaking point to where it's actually cheaper to start over than it is to add that next incremental feature and continue to deliver value? So that's A, quality number one. Probably more than half the sessions that you're going to attend this week are going to somehow be addressing this point. And then there's this wild success coupled with system failures. Can we deliver systems that are able to not only survive but also thrive amidst turbulent conditions in production? So can we throw whatever stress we can imagine at a piece of software, and not only does it continue to work, but it continues to provide satisfaction to the customer? They continue to not only use the software, they enjoy using the software, even though there are failures happening all over the place, but they never actually know about it. So I think we would probably agree that if we could get these two things right, we're doing well over average for the industry, right? So how do we know that we have this stuff? So this is where it gets hard, and this is where my conversations with the teams that I work with around the globe tend to slow down and get more interesting. Because everybody can agree, I want those qualities, and then I can ask the question, well, how do you know that you don't have them now? Well, we just know. Okay, well, that's not very scientific. How can we measure that, and how can we figure out, well, where are we right now, so that when we go change things and try to make things better, we know which direction we went on the scale. And then ultimately we can pick a spot that we want to end up. So what are some proxies that we can use to measure these qualities? I think we know some of these already, but we don't necessarily measure them well. So when I'm thinking about innovation, I'm thinking about really 4 types of things. 1, lead time. How long does it take to go from somebody having an idea that we think is going to make us some money to we're actually making money? And is that a somewhat predictable thing? Or is it all over the place? Some ideas take forever, some ideas don't take that long, and when we get started, we don't really know. We want to get to where lead time is something that within some small range of variation, we kind of know. I can, the tagline of an idea in the mornings, in production in the afternoon, that's what this is all about. Now, inside of lead time, there is cycle time. So we kind of chop off the part at the front end where we have an idea and we figure out what we're going to make. And we start with, okay, we're going to go make the thing. and then we're going to deliver it into production. Now this one we have a little bit more control over the predictability of. Once we kind of know this is what we need to go do, we probably have a decent sense of how long it's going to take to actually create that thing. And then we especially should know, once we've created that thing, what's it going to take for it to flow through our continuous delivery pipeline, run all the tests and checks and compliance and regulations and all the stuff that we expect have to be there before we can go into production. And ultimately we land that thing in the cloud somewhere, and then people are able to start using it. We should have that tightened down fairly well. That should look almost like a manufacturing assembly line, if you will. In fact, that's the only thing in software development that really can look like an assembly line. But we don't want to stop here. There's a couple of these that I say all the time. I had to invent names for them this morning. And so the next thing we're going to talk about is inverse lead time. So I've delivered a thing, and hopefully I'm in some way gathering feedback from the users of my system, from the business owners, from the customer, from whoever has a stake in this software, and I take that feedback and I turn it around into input into the front of the pipeline. We don't talk about this that much. Say, okay, there's some magic source of ideas over here, and we flow them into the pipeline, and we're so worried about this forward direction that we don't necessarily talk about the reverse direction very much. But this turns out to be one of the biggest things that we have to worry about, because if this thing is measured in weeks or months or years, it doesn't really matter how fast we can flow forward. And then this is my favorite new metric. It's what I call the trash ratio. So if, quote unquote, agile software development is experimentation, what are we experimenting on? We're experimenting on our ideas. What are we trying to figure out? Was it a good idea or was it a bad idea? We tend to treat these experimental outputs like capital. Once we create a piece of software, it doesn't really matter if it's a good piece of software or it's a crappy piece of software. We keep it, and we take care of it, and we continue to pour into it, as opposed to, hey, we should have never built this thing before in the first place, let's throw it away. And I don't know about you, but more than half of the ideas that I have, and that's being generous, are not very good ideas. And so if I'm not actively throwing those things away, that means that I'm spending effort on those things, which means that effort is not being spent on continuing to work the innovation machinery. So I think these four things are pretty good. Let's talk about resilience. So I want to touch on two things, and you'll probably hear about these from a lot of other speakers this week: service level objectives and steady state metrics. So service level objectives come from the site reliability engineering, the SRE conversation, and there are not now just one but actually two fantastic books that you can get your hands on to read about. On the left-hand side, sort of, this is how it works inside of Google, and there's a lot of interesting principles there that you can apply, but there's also a lot of things that feel a little bit specific to that context and are harder to apply. And then on the right, well, here's what it looks like to translate all of that stuff practically into other contexts. How do I actually go about figuring out what my service level indicators should be? How do I actually design service level objectives, and what does that conversation look like between the business and the developers and the operators and everybody in between? So, two things. We need indicators. We need to measure things. We need some kind of quantitative understanding of what is the level of service. So one of the things that we love to point at is request latency. So what is the request latency over X time period on cluster Y right now? Service level objective is, well, what's acceptable for that? What is the goal? What is the range of values that we're looking for that service level indicator to live within? Pretty simple, right? Now, it seems simple, but I will tell you that 90% of the people I ask, what are your service level objectives? The answer is, I don't know. So we can get better at this. We can also get better at not looking at averages, because averages are interesting if you're dealing with a normal distribution. If you're not, they're not only not interesting, they're misleading. So we want to focus on distributions, and we want to focus on those long tails. So this is a graph that I stole right out of the SRE book of latency. And it shows us that it's entirely possible for the average request to be pretty fast, 50 milliseconds, that works. But then the long tail is 20 times slower. So we're now measuring response time not in milliseconds, but in seconds. In fact, 10 of them. Now, if you are in that long tail as a user, you don't really care if everybody else is having a really good average day. Now you say you don't know what to measure, and when I'm talking to somebody from an operations background, they know more things that they want to measure than maybe they necessarily should. And I find that a lot of that conversation amongst the quote-unquote thought leaders is, okay, here's how you actually stop measuring so much and focus on what's really important. When I talk to developers, usually I'm being asked the question, well, just give me the list of things that I can measure so that I'll get it right, because that's not part of their background. And so there is an offering from Google of, well, if you don't know what to do, here are 4 things. We've talked about latency already. Of course, latency is not really that interesting if we don't compare it with traffic. If your system's really fast when you have one concurrent user, yeah, I hope so. Error rate, latency is not that interesting when all of your return codes are 502. Those actually often tend to be very fast. So we have some things that add meaning. And then saturation point is the one that's less obvious, but pretty darn important. So everything's bound by something, right? Some things are processor bound, memory bound, storage bound, I/O bound. A lot of things, probably most of the things that we're building these days. And how full are you with respect to the thing that you're bound by? How much usage of that resource can you tolerate being consumed before the server melts? Knowing what that point is, and then knowing what is the acceptable safe threshold that you can walk up to so that you can still reverse the damage when you turn whatever dial it is to make things better. So this is where my conversation used to stop. But then I got interested in this concept of steady state. So steady state comes from chaos engineering, and we're going to talk a little bit more about that later on. Steady state is an externally visible metric. So again, put yourself in the shoes of the customer who's coming to the system, and this is something that they can observe, maybe not directly, but the thing that I'm measuring is indicative of their experience, and it also has a fairly low degree of variation. So Netflix picked one called SPS, or successful streaming starts per second. And what are we looking at? Well, every time somebody says start watching, and that actually starts a successful stream, we measure that. And one of the things that they noticed is that we are so predictable as humans in our watching behavior that there's very, very little variation on a daily or weekly basis in SPS, given a time zone. So the peak of this is somewhere around the dinner time, between dinner time and bedtime, kind of prime time hour, and the trough of this is somewhere slightly before where we're trying to get up and theoretically go to work the next morning. Now, there are two graphs overlaid here. I can't remember if red or black is last week and which one's this week, but they are 2 consecutive weeks overlaid. And if they weren't 2 different colors, it would be pretty hard to actually tell that there were 2 graphs there. So very low degree of variation. Why is this a good metric? Well, ultimately, it is a proxy for the most important thing that Netflix does. You know, Netflix does a lot of things other than stream video. But if they can't stream video, it doesn't really matter what they can do, right? So when we're thinking about our systems, you ought to be able to answer a couple of questions and then find some metric that can proxy that. So first of all, you know, what is the most important activity that you do? Do you have it? Is it here in your head already? It should be, right? If it's not, we need to solve that problem. We need to understand, how does the thing that we're working on tie to some context that this is the most important thing that the business does, and this is how we plug into it. And then, you know, what single indicator could you use to approximate it? Now, you don't have to have this one come to mind immediately, but start thinking about, okay, this is the most important thing that we do. Is there something that we can measure that will tell us that we're doing that? And something that when we're not doing that is going to start to vary significantly from the norm. One last thing on measurement. Time to recovery. What is time to recovery? It is the lead time from when you discover that you have a problem till that problem is fixed. The cost of failure can pretty much be directly proxied by that. So it doesn't really matter how well we can tell what the system is doing, again, if we can't actually reduce the time it takes from when we discover something's wrong till, well, that thing is no longer going wrong. So this is kind of how we're going to measure that we have these qualities. So innovation and resilience both can kind of be proxied by some notion of how long does it take from discovery to delivery. Okay, last thing, which we're doing well. I've got about 30 minutes left to figure out how to create this stuff. That was where I hoped I would be. So we're bending but not breaking so far. How do we create these qualities? So let's come back to quality number 1. Can we continuously deliver incremental value to the business through software? Well, let's go back in time and see. So we're going to go back to 1971. Because we were trying to figure this out decades ago. And to be perfectly honest, we did figure out decades ago what we needed to do. We just promptly took that information and put it on the shelf and ignored it. But it's captured in this paper, and this paper Googles incredibly well. You can get a PDF of this from about 50 different sites easily. Sometimes they move around. I don't direct link to them anymore. I just say Google it, but So on the criteria to be used in decomposing systems into modules. Sounds very stuffy, but it's remarkable what was done that we're still trying to do. So the paper starts out, and it talks about modularization. Cool, architecture terms. We're finally getting there. And why do we want to modularize? Because we want to improve the flexibility and comprehensibility of a system while allowing the shortening of its development time. Who doesn't want that, right? Like if we can do that, we can innovate. And you know what? They figured out how to do it. The progress at that time was being made. Number one, we can have one module be written with little knowledge of the code used in another module. That sounds suspiciously like encapsulation. 2, modules to be reassembled and replaced without reassembly of the whole system. That sounds suspiciously like polymorphism. Now the funny thing about this is these concepts were being discussed when object-oriented programming was still in its infancy in academia. None of the stuff that we were, those of us that have been around the 20 to 25 year mark were being ingrained with in school, none of that stuff really existed yet, and yet we were talking about it, which of course means that these qualities also have nothing to do with OO. They're just there. OO is one way to get them. So let's talk about decomposing software. We're going to build an online store. So here we are, and we've got some business things that we need to go do. Capabilities. That's probably what minimum viable product, like if you can't do one of these things, you're probably not a very good online store. So we're going to do these things. How do we typically approach building a system like this, even today? Even if we're doing microservices, what do? We make groups of people that look like things that we're going to make. So I've got some data-looking people, and I've got some service-y, business logic-y looking people over here. I've got some UI people over here. And let's put them all in tribes, and let's let the tribes do their thing. So what do the data people do? Well, they make a schema, and then they maybe put some objects on top of it. What do we do with that thing? Well, we take all those business capabilities and we stripe them across the layer. So what is that layer responsible for? Everything with respect to data, with respect to our business. And then we build another layer on top of it, and we do the same thing. What is the service layer responsible for? Everything. Then we build another layer on top of that. What do we put in there? Everything, right? And then we take that stuff and we zip it up in a little monolithic deployment, and we're kind of done. So why do we build layered architectures? What 3 words should you be screaming at me right now? Separation of concerns. It didn't take half a second for it to come out. Now, why do we want to separate concerns? Well, we want to separate concerns because, hey, if I can hide what's going on in that data layer from everybody else, then I can change what's going on in that data layer without anybody else knowing or caring. That's the party line, right? Now, what is the most cited example of why you build layers? But what's loosely coupled? What can you now do? Yes, you can swap out the database. How often do you actually do that? So we've got this layering that helps us to do something that we never do. Now, we go build a new feature. How many of these layers do we have to touch? All of them. So we haven't done anything to help building features. In fact, all we do is coordinate amongst all these layers and all these groups trying to get things done. Now, they talked about this in the paper. They called it functional decomposition. And we had our 3 things that we cared about. We want to change things and be able to continue to do that. We want to be able to have independent development. You don't have to know about other things. We want to be able to comprehend the system. So how did we do? Well, change is still hard because The change is spread across all the modules. Independent development is still hard because we have to figure out how to pass information between all of these layers, and we kind of have to agree on how that's going to work. And in fact, we usually do that with libraries at best. We're passing code up and down that stack. And so anytime we want to change any of the layers, we have to change the interchange format. And then comprehensibility, you have to know something about the whole system to understand any of it. So we're not doing so well. Let's refactor to capability decomposition. So what do we do first? Bye-bye layers. They weren't doing us any good anyway. What do we do instead? Vertical slicing. In fact, this is a really okay place to stop. In fact, if you don't need to go any further than this, don't. You're starting a new system, this is actually a really good place to start. Because why? Well, what if you get the boundaries wrong? Is it easier to fix that mistake now or now? Is it cheaper to fix that mistake in the previous picture or in this picture? You think this is easier? No. The other one's easier. Okay. Because if we got that backwards, the whole rest of the talk's not going to work. Can we stop here? Only if you don't care about consistency. I like that. We can stop here. We probably shouldn't. So we'll go one further. And that made that look really simple, but that part's the hard one, right? And I don't have time to talk about that today. Somebody will. Go find a session about Kafka and you'll get that covered. I'm joking. What do we do with the people? We need to know, right? 27 bus number ones. Let's align them with the vertical slices. So now we have one dimension of change for our team structure, code, data, and they're all related. Theoretically, this product catalog team on the left ought to be able to do almost everything that they need to do with no coordination with any of the other teams. Not everything, but at least with respect to what's going on inside the box, they should. So what does capability decomposition get us? Well, change, usually isolated to a single module. Check. Independent development, we've got abstract interfaces between the services, but we don't have to actually pass core artifacts between them. Check. Comprehensibility, you can understand payments without understanding shipping. Cool. So this was kind of the conclusion of the paper, was that capability decomposition is superior to functional decomposition because it's actually aligned with the dimensions of change that we really encounter. Now, when we're designing a system like this, we really have to think about two sides. And so I like to talk about the peanut butter and the jelly of architectures that bend but don't break. So what's the peanut butter? The peanut butter is the thing that is the foundation of the peanut butter and jelly sandwich. Like, I'll eat a peanut butter sandwich without jelly. I'm not really so fond of a jelly sandwich without peanut butter. My kids are, but not me. Not a lot of optionality in the peanut butter layer. You know, it's kind of like creamy or crunchy, a little bland, but peanut butter's kind of peanut butter, right? This is the domain model, and this is where we're going to apply domain-driven design. Now, lots of optionality in the jelly layer, right? I can do grape, I can do strawberry, I can do peach, I can do apricot, whatever your fancy happens to be, mixed fruit, it's all there. The type of technical architecture application that we can lay on this domain model is where we get that resilience in terms of innovation. And so the tool that I like to throw here is hexagonal architecture. So let's do the fastest coverage of both of these topics I've ever done. Domain-driven design. We start with strategic. We're at 35,000 feet. Big picture point of view. What are we trying to do here? We're trying to figure out one of the most popular and poorly understood terms in the industry today, that of the bounded context. What is a bounded context? It is a bounded place where a particular language of domain modeling is spoken. You've probably heard it called the ubiquitous language. So you see there's a different language being spoken in each of those colors. And that language is contained and internally consistent within that context. When I use the word, say, customer, and you use the word customer, we mean precisely the same thing. And this is what bounded contexts really are. And this is the heart of everything else that we're going to do. If we don't get the language right, it doesn't really matter what else we do. We're going to get that stuff wrong because we're building it within the basis of a confusing model. And then strategic design also covers, well, how do we actually take these bounded contexts and bring them together? Then we come down in elevation, say about 10,000 feet. We start talking about tactical design. So this is where we start speaking the ubiquitous language within each bounded context. We start talking about business invariance, policies, transactions, state, persistence, all the stuff that we want to get to first before we got the language right. So we get the language right, then we jump in there and we start speaking these things in terms of that language. The central concept of this happens to be the aggregate. The aggregate is also a funny name for something that we talk about, but we don't talk about very rigorously. So what lives in here? Now, we've got a bunch of objects. They're treated as a single unit. They have a root. Think of an order and its line items. So we only come through the order. The aggregate is responsible for maintaining all the business invariance associated with order, and we've got a bunch of rules for how that is done, but I don't have time to talk about them today. The program committee rejected my domain-driven design talk. Joke's on them. Atomic unit for any transactional behavior. This is super important. Do transactions go beyond a single aggregate? No. That's easy. That's a rule that we can hold on to and guide a lot of decisions that we're trying to make. And then these things often turn out to be state machines. Now, what are we going to do with these aggregates? Well, we're going to shove them into a hexagon. When we said that microservices were hexagons a few years ago, we actually kind of got it right. We just didn't know it. So I've got this thing that we'll call an application service, and we're going to shove into it a domain model. So this is where all that domain-driven design stuff is happening in terms of just plain old code. Like if you just want to do some plain old Java object programming and not worry about frameworks and technologies and databases and stuff, this is where you get to do that. And then we wrap that in an outside-inside fashion with what we call ports. These are generic entry-exit points. If we're writing Java code like we do at this conference, these are interfaces, right? And so the only way you get to touch the domain model is through an interface. Well, where do the implementations of that come from? Adapters. That's why this is also called a ports and adapters architecture. So these are the specific implementations, and this is where we get a lot of our optionality. So we take that domain model, and there's our aggregates, repositories, domain events, all that fun stuff's happening in there. But the domain model is peanut butter. Doesn't change over time with respect to what types of databases or communication wire protocols, serialization mechanisms that we're using, because that is existing in the outer ring of the adapter implementations. So you want to do REST, you want to do SOAP, you want to do both so that you can integrate with older systems and newer systems. You can do that there without polluting your business logic with those concerns. Same thing, we can vary messaging formats, we can vary persistence technologies. I've got about 40 more slides that I could do on that, but again, we only have 10 minutes left. So what everybody wants to know is, what does this have to do with my microservices? Almost there. I'm going to give you a golden rule. My software module is somewhere between the scope of an aggregate and a bounded context. So there's my happy little software module. Where does it live? Aggregate on the left. So it's at least as big as a single aggregate, right? Can I have an aggregate split across modules, which might become microservices? No. Why? Because now I've got distributed transactions. That's gross. I'm not going to do that. So this is our lower bound. Upper bound is what? Bounded context. Why? Because we don't want to speak multiple languages inside of a single module. So we've got business invariant transaction scoping on the low end. We've got language scoping on the high end. So could have multiple modules in a bounded context, but we're not going to extend beyond that boundary. Could have multiple aggregates within a single module, but we're not going to go less than one. This is the sweet spot. How do you decide where to go? That's more art than science at this point. And so then we come to the spectrum. Almost everything that we do as architects is going to be on a spectrum, and we've got to get out of this notion of dichotomies. The dichotomy right now is big ball of mud monolith evil, microservices good, right? Nothing useful in between whatsoever. Wrong. So we shouldn't build the big ball of mud, and we probably shouldn't go microservices crazy either. The extremes of the spectrum are probably not where we want to live. There's probably something somewhere in the middle. It could be closer to microservices, it could be closer to monolith, but at the end of the day, we want to follow good, solid software engineering modularity principles inside of that spectrum. You start to look at what's going on inside that friendly modular monolith in the middle. Everything that you can do inside that modular monolith is often something that you'll be told you have to have microservices in order to get these qualities. Now, if that were true, that would mean that there was no software that was designed well before 2013. So we're probably okay. But once we know that we need, hey, this thing needs to be individually deployable, upgradable, replaceable, all the things, then we say, I want to eject that hexagon from the modular monolith and make it into a service. And because of my outside-inside rings, I should be able to vary the communication that I need, vary the persistence that I need to do that without disturbing the hard parts, which is that business logic that's aligned with that domain model in the middle. Now, again, is this easy? No, it's hard, but it's a path forward. Okay, I have 5-ish minutes to cover everything else. This isn't going to work, but we'll do our best. Can we deliver systems able to survive and thrive amidst turbulent conditions like this 5-minute period of time? So resilience, I can actually go through this pretty fast because you don't need me to explain these things to you. You can read about 20 books on each of these. They're well understood. They've been there for a long time. They're just not evenly distributed as far as our knowledge. Basic things like using timeouts. Does every engineer that works on code in your company understand when and how to use timeouts appropriately? Yes or no? Okay, start here. If we can get this right, then we can start to layer things on top of that, like retry logic. If I've got a system that, I have to deal with, but it's not terribly scalable and it's not going to be that legacy stuff that you still have to talk to while you're doing your modernization, digital transformation, whatever that is, right? Sometimes we need to try things a few times because sometimes that system's a little overloaded and needs us to give it a break. But we can't build retry logic without timeouts. Bulkheads. This is one of the most powerful patterns out there that not many people talk about. So we build ships with these bulkheads. They're walls that extend top to bottom, and they have doors, but they're sealable doors. Why do we have that? Well, we have it because sometimes we get holes in the side of ships, especially when they're doing battle. Now, if you didn't have bulkheads and you just had one big compartment, what is the scope of the flooding when you get the hole in the side of the ship? Total, right? What happens to the ship? Usually it's going to sink, and that's not what we want. So if we have bulkheads, we can start to seal these compartments, limit the scope of the flooding, and probably in a lot of situations, we're able to keep that ship afloat. Now, what does that have to do with software? Well, we're talking about dividing things up. We can divide things along the dimension of thread pools. We can divide it along the dimension of service boundaries, availability zones, regions. And so we can start to bulkhead our system with respect to interesting failure modes that we've identified. Of course, there's circuit breakers. This is the one that everybody loves to talk about. I'm sure at least 3 sessions are going to cover this, so we'll move right on. What do you need to read? Mike Nygaard finally updated his book last year. And I say it's even better now than it was before. So I highly recommend that you get your hands on that one. Okay, last 2.5 minutes, we're going to embrace chaos. For us to understand and apply chaos, we need to go back to the notion of the socio-technical system. The system would naturally experience chaos, but if we're going to do chaos engineering, we need to inject chaos intentionally into the system. And so that involves some amount of human effort and application. So fun website that you can go read sort of the manifesto of this, Principles of Chaos Engineering. But basically the idea is that we're going to do science on our system. We're going to figure out a hypothesis about how our system's going to behave, and then we're going to throw chaos at the system and see what happens. And either our hypothesis is going to be validated or it's going to be invalidated. And so this is about all of the unknown unknowns that we have in our software. This is why we cover the resiliency patterns first. You don't start doing chaos engineering if you know that when you turn on the chaos monkey, your whole data center is going to explode, right? Go fix that stuff first. You say, okay, as far as we know, we have a resilient system. No, you don't. Now it's time to figure out what's left to do. So 5 principles of chaos engineering. We've already talked about the first one a little bit. That steady state behavior is important because that's what we're going to come to first. We need that business-facing metric that's got a predictable pattern that when we do something to the system, like invoke chaos, then it's going to fluctuate significantly. And in fact, if we can get this metric to a point where we can literally divide our production incidents into steady state behavior impacting or not, then we have a very good idea of what production issues are highest priority and which ones are not. If we don't have this, it's a little bit more of a guessing game. Now, once we have this, what's our hypothesis? Well, it looks like this now. It's always going to look like this. Then what do? We break stuff. All these things happen in the real world, and this is just a subset of the possible things that can go wrong. So we're going to throw this kind of stuff at our system. Where are we going to do it? We're going to do it in production. Why do we do it in production? Because if you're lucky and you have a lot of money, you might come very close to having two environments that are production ready that look exactly the same. But you probably don't. It's impossible to duplicate the traffic. Even if you gather all the traffic you've had up to this point and replay it, you don't know what your user is going to do tomorrow, and what they do tomorrow might be the thing that actually breaks your system. So the only place you can really truly know how the system behaves is the socio-technical system that is production plus users. You got to automate. Why? Because you want to keep running these same experiments over and over and over and over again. Once you have fixed something, you want to continue to apply that same chaos. Why? Because theoretically you fixed it. If you change the system and you unfix it, you want to know. We want to get to the point where the types of chaos that we're injecting are routine, boring, mundane events. Of course, you need to minimize the blast radius. If you start intentionally attacking your production system, you're going to break something that's going to piss off customers. It's going to happen. So try to minimize and contain the fallout that comes from that. And as a very quick intro to this, again, I give a whole 90-minute talk on just this topic, but I wanted to squeeze it in. This is a great and I think still free book that you can get your hands on that sort of the original chaos engineers at Netflix put together. So, this is where we were. Hopefully we know what architecture is. Hopefully we know what it means to bend but not break. We know about stress. We know what we want to happen. We know how to measure it. And hopefully we know a little bit about how to create it. And I apologize that I am now officially 4 minutes over time. But hey, we're going to bend but not break. Thanks.